Welcome to Edu Aspirants, our YouTube channel for competitive exams. In the series of videos on physics, let us see what we have for you in the first of two videos on OPTICS-1, ray optics. So these are the topics which we will cover. First, refraction of light, laws of refraction, principle of reversibility of light, refraction through a parallel slab, refraction through a compound slab, apparent depth of a liquid, total internal reflection, refraction at spherical surfaces, introduction, assumptions and sign conventions, refraction at convex and concave surfaces, Lensmaker's formula, first and second principal focus, thin lens equation, Gaussian form, linear magnification. Refraction of light. Refraction is the phenomena of change in the path of light as it travels from one medium to another when the ray of light is incident obliquely. It can also be defined as the phenomena of change in speed of light from one medium to another. As we can see in this diagram, light is traveling from rarer to denser medium. These are the normals. These are the angle of incidence and angle of refraction. So laws of refraction of light. First law, the incident ray, the normal, the refracting surface at the point of incidence and the refracted ray all will lie in the same plane. Second law, for a given pair of media and for light of a given wavelength, the ratio of sine of angle of incidence to the sine of angle of refraction is a constant, that is Snell's law. Numerically, it can be written as mu is equal to sin I upon sin r. The constant mu is called refractive index of the medium, I is the angle of incidence and r is the angle of refraction. Tips. Mu of optically rarer medium is lower than that of denser medium is higher. Mu of denser medium with respect to rarer medium is more than 1 and that of rarer medium with respect to denser medium is less than 1. Mu air is equal to mu vacuum is equal to 1. In refraction, the velocity and wavelength of light change, but in refraction, the frequency and phase of light do not change. Numerically, we can write A nu m is equal to Ca upon Cm, where Ca is the speed of light in air and Cm is the speed of light in medium. And A nu m is equal to lambda A upon lambda m, where lambda A is wavelength in air and lambda m is wavelength in medium. Principle of reversibility of light. As we can see in this diagram, we have two medium, rarer and denser, and we put a mirror in denser medium. When light ray goes from rarer to denser medium, it reflects from the mirror and traces the same path as it is. These are the angles, angle I and angle R. If we can write A nu B is equal to sin I upon sin R as per Snell's law, and B nu A is equal to sin R upon sin I. If we multiply these two, we will get A nu B into B nu A is equal to 1, or A nu B is equal to 1 upon B nu A. If a ray of light, after suffering any number of reflections and or refractions, has its path reversed at any stage, it travels back to the source along the same path in the opposite direction. A natural consequence of the principle of reversibility is that the image and object positions can be interchanged. These positions are called conjugate positions. Refraction through a parallel slab. So this is a parallel glass slab of thickness T. The light rays traveling from rarer to denser medium and from denser to rarer medium. These are the normals. This is denoted by Y, angle I1, angle R1, I2 and R2. This is angle is delta. So A nu B can be written as A nu B is equal to sin I1 upon sin R1. B nu A is equal to sin I2 upon sin R2. But A nu B into B nu A is equal to 1. Therefore, sin I1 upon sin R1 into sin I2 upon sin R2 equal to 1. It implies that I1 is equal to R2 and I2 is equal to R1. Since I1 is not equal to R1 and I2 is not equal to R2, as per the diagram, we can see I1 is equal to R1 plus delta and I2 is equal to R2 minus delta. Now lateral shift. Y can be written as T sin delta upon cos R1, or we can write Y is equal to T sin I1 minus R1 upon cos R1. Special case. If I1 is very small, then R1 is also very small. That is sin I1 minus R1 is equals to I1 minus R1 and cos R1 is equal to 1. Therefore, y can also be written as t I1 minus R1 or y is equals to t I1 1 minus 1 upon a nu b. Refraction through a compound slab. In this diagram, we have three medium. First one is rarer, second one is denser of refractive index mu b, third one is denser of refractive index mu c. Now light rays traveling from medium A to medium B to medium C to medium A. These are the normals and these are the angles I1 R1, R1 R2, R2 and I1. So A nu B is equal to sin I1 upon sin R1, B nu C is equals to sin R1 upon sin R2, C nu A is equal to sin R2 upon sin I1. If we multiply these three, we will get 1. A nu B into B nu C into C nu A is equal to 1, or A nu B into B nu C is equal to A nu C, or B nu C is equals to A nu C upon A nu B. Apparent depth of a liquid. We can see a container filled with water. There are two medium. First one is rarer of refractive index mu A and second one is denser of refractive index mu B. Now we place a coin at the bottom. When the coin rays are passing from denser to rarer medium, it will go away from the normal. So for an observer, the coin will appear at a position O dash. This is HA, that is apparent depth. This is HR, that is the real depth. This is angle I, this angle is R. So B nu A is equal to sin I upon sin R, or A nu B is equal to sin R upon sin I. A nu B is equal to HR upon HA, that is equal to real depth upon apparent depth. Apparent depth of a number of immiscible liquids. HA can be equal to summation I is equals to 1 to n HI upon mu I. Apparent shift. Apparent shift is equals to HR minus HA. So HR minus HR upon mu, HR bracket 1 minus 1 upon mu. Tips. If the observer is in rarer medium and the object is in denser medium, then HA is less than HR. To a bird, the fish appears to be nearer than the actual depth. If the observer is in denser medium and the object is in rarer medium, then HA is greater than HR. To a fish, the bird appears to be farther than the actual height. Total internal reflection. Total internal reflection, TIR, is the phenomena of complete reflections of light back into the same medium for angles of incidence greater than the critical angle of that medium. As we can see in this diagram, there are two medium, denser glass of refractive index mu G and rarer air of refractive index mu A. Now we are just increasing the angle of incidence. In this case, as we can see that the angle of incidence is equal to IC, that is the critical angle. For it, the angle of refraction is 90 degree. If we further increase the angle, then no refraction will take place, only reflection of light occurs. This is the phenomena of TIR. So the necessary conditions for TIR are: first, the incident ray must be in optically denser medium, that is light ray must travel from denser to rarer medium. Second, the angle of incidence in the denser medium must be greater than the critical angle for the pair of media in contact. Relation between critical angle and refractive index. Critical angle is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree. G nu A is equal to sin I upon sin R is equal to sin IC upon sin 90 is equal to sin IC, because sin 90 is equal to 1. A nu G is equals to 1 upon G nu A. Therefore, A nu G is equal to 1 upon sin IC, or sin IC is equals to 1 upon A nu G. Also, sin IC is equals to lambda G upon lambda A. Red color has maximum value of critical angle and violet color has minimum value of critical angle, since sin IC is equals to 1 upon A nu G is equal to 1 upon A plus B upon lambda square. Applications of TIR. First is mirage formation. Second is looming. Third is totally reflecting prism. Fourth, optical fibers. Fifth, sparkling of diamonds. This brings us to the end of the first video of the 2 videos on optics. The second video will be uploaded soon. Please subscribe, like, share, and do press the bell icon for updates. Best of luck for your forthcoming exams. Thank you.